Hello, this is MA 255, section 12.5, and we're going to talk about making the vector equation of a line. I call it the parameterization of a line, and then we're going to talk about the parametric equations. For example, one of our homeworks might ask us to find the vector equation of a line through the points, and then we'll be given a couple of points. And then maybe they'll ask us to list the parametric equations. One thing to look out for is, in this particular question, it doesn't specifically say if you have to write it so that you go from 0.12 to 47, or if you need to start at 47 and go to 12. So this is, sometimes it doesn't matter, but sometimes the textbook or question or even in the context, will ask you to do it in one direction or the other, so just be aware of that. So the vector of equation of a line, usually our textbook uses R, and that's pretty common. R equals R naught plus T times V vector. This T is the input for this vector equation, and this is called the parameter. And so usually we use t because t equals time. When we parameterize a line, usually, or any curve, usually we're parameterizing it in terms of time. It doesn't have to be that way, but that's the most common. So what I'm going to do is rewrite this equation a little bit differently. Instead of it being in the form that the book has given us, I'm going to write it a little bit different. So I'm going to put the V first, and then the T, and then the R vector initial. And so the reason I'm doing that is I want to draw a parallel to something you already know, which is the equation of a line given in point or slope-intercept form. So the reason I've done this is the first thing I want to draw some similarity to something you already know is this x and the t. So x is the input, and we already knew that, and m is the slope, and then this b is when x is equal to 0, and that then is the y-intercept, right? So that's, we're used to those things. Now, there's not an exact correlation between these two, I suppose. So if we can remember what we're doing with y equals mx plus b, then figuring out this vector equation of a line is quite easy. If we remember that when x is 0, then we get the b. That's what happened before. And so if we think about when t equals 0, then we get the RO. Okay, and then we have to find the v, but finding the v is not difficult, and it's not exactly like finding the slope, but it's very similar to finding the slope. Okay, so let me rewrite my 2 points here, 4, 7. And the other point was 1, 2. So the first thing we have to decide is where we want to start and where we want to end. And I'm going to really quickly draw an XY plane here. And let's see, this would be point 1, 2 would be here. And then 4, 7, so this would be 2, 3, 4. This was 2, so 3, 4, 5, 6, 7. We'll put that up here. So those are my 2 points. Okay, and let's say I decided that I wanted to start at 1, 2 and go to 4, 7. So this is my start, and this is my end. And when I find my v vector, it doesn't have to be done this way, but this is the algorithm that I use, and it looks the nicest, I think, is I start with the end and I minus the start. And this method is going to parameterize between those 2 points from t equals 0 to t equals 1. It doesn't have to be done this way, but I like doing it this way. And the reason I like doing it this way the most is because I can easily multiply in my head by 0 and 1. You could choose some other numbers, but 0 and 1 are the easiest to do. So that's the way I do it. So if I'm going to start at 1, 2, and end at 4, 7, so I'm going to make v equal to, so then I do the x end minus the x start, comma, the y end minus the y start. So here we go, 4 minus 1, comma, 7 minus 2. Because once again, remember, let me write it here again, our 2 points were 4, 7 and 1, 2. And we're going to start at 1, 2 and end at 4, 7. That's the way we've decided. And so now I have 3, comma, 5. So that's my v vector is 3, comma, 5. And then my r initial vector, where I'm really doing is starting at the origin, and I'm ending at the point 1, 2. That's if I've decided to start there. So I'm doing at the point 1, comma, 2, and I'm minusing the end, or that's the end, and the start is the origin. So let me draw a picture up here. I want to make this vector right here go from the origin to the point 1, 2. And I'm going to make that my r initial because that's where I'm starting. If I was starting at 4, 7, I would go from this point up to 4, 7 as my initial. But I want to start at 1, 2, so I'm going to start at the origin and end at that point. So if I wrote this out, well, it's end minus start, right? So I do 1 minus 0, comma, 2 minus 0. Now, folks, you never, ever write this again, right? You just look at where you want to start and you write down the point in with vector notation, right? Because you know that the r initial is these zeros, right? So you're always going to be minusing 0. So no one writes this step out. They just write, oh, where's my starting point? I'm going to write that as a vector. Okay, so now you just put it together and you do r equals t times v plus where I start. I like writing it that way versus the other way that the book writes it. And so t times v was 3, comma, 5. And plus r, which is r initial, which is 1, comma, 2. You could write it the other way, of course, which is 1, comma, 2, plus t times 3, comma, 5. And look what happens here. If t is equal to 0, then my r equals 1, comma, 2. Because the t is equal to 0, and so this first term is going to go away, and I'm left with just 1, comma, 2. If t is equal to 1, and this is the version I use. Again, I choose to run from one point to the second point from 0 to 1. I would have 1 times 3 comma 5 plus 1 comma 2. So this 1 times 3 comma 5 plus 1 comma 2. And when I simplify that, I get 3 comma 5 plus 1 comma 2 in each of these vectors. I put the components together, I get 3 plus 1 and 5 plus 2. And of course, that's 4, 7. Right? That's where we wanted to go. And if you look, what happens is this step 3, 1, 5, 2, you look up here to when we're putting things together, and we're sort of doing the reverse, right? So that's why that's working. We're doing the reverse of what we did with the n minus start. We're doing the other direction. Now we're adding them together. So we get this 4, 7, and sure enough, that's the point that we were ending at, was 4, 7. So if I wanted to extend the line out, I would use, t equals all the numbers. If I wanted to graph the whole line from 0 to 10, well, I would just write this as, well, I'm using all the numbers from 0 to 10, right? And I would plug in 0, and I'd plug in 1, and I'd plug in 2, and I'd plug in 1.5, and 1.6, and 2.7. I'd plug in all these values all the way up to 10. And what I would get then is a line that started here and went off past a ways, right? And if I wanted it to go before that, I would do something like, let's do from -5 to +5, right? And so now when I graphed the line, I would plot the points like down through here, right? So -5 to +5. When t was equal to those, you'd get all those points on the line. So try that, experiment with that on your own, make that work for you. Plug in different values of t and point them on a piece of graph paper and connect them and see that indeed it makes these lines. Okay, let's finally talk about these parametric equation business, right? So that's the parametric equations. So one way to view this R vector is by the components. So in this case, it would be x and y in 3 dimensions, or in R3 is a fancy way of saying that. This R vector, my R vectors keep looking like V vectors, don't they? Let me try to make that nicer. This R vector would be x, y, and z. Okay? And the way we could write that would be to say that the x, y, and z is equal to the x initial plus t times a, the a component, and the y initial plus t times the b component, and then the z initial plus t times the c component. We could write it that way. So really what we would be doing, x is equal to the x naught plus t times a, and y is equal to y naught plus t times b, and z is equal to z naught plus t times c. So let's look at our example that we have with our equation from up above. Let's write that out. So I have my r equals t times 3 comma 5 vector plus the vector 1, 2. So the parametric equations, the x part would be 3t plus 1, and the y part would be 5t plus 2. Those would be my parametric equations. And if I wrote them out in the vector itself, I would have r equals 3t comma 5t plus 1 comma 2. And that is 3t plus 1 comma 5t plus 2, each component written out piece by piece. Now again, when you're doing it, I just look at the actual vector itself and I say, oh look, it's 2 times t times 3 and t times 5. So the first component multiplied by t, and then the first component is 1 with this plus. And then t times 5, 5 times t, and then plus the second component, which is t. But if you actually wrote it out, this would be the x parts would be here, and the y part would be there. Okay, I hope this helps. If you have any questions, please let me know.